So the last subject we're going to cover in thermodynamics is that of thermal laws. And the problem is that we don't have an isolated system. Every example that we've looked at, and most of the ones that you'll actually find in physics, deal with an isolated system, and you assume that no energy is transferred to the outside surroundings or from one system to another. So in our example that we saw of cooling down soda in the summer using ice, well, our system was the soda and the ice together. But we know that the sun is still beating down on this. We're still getting energy in from the sun, and there's the air around it, and we're losing energy, or we may be picking up energy or losing energy to the air. We put our hand on this, on the glass. How much energy comes from our hand? Well, what we're going to do is look at how we can deal with thermal energy from one system to the surroundings, or from the surroundings to the system. And the way we're going to deal with that is we're going to actually look at the rate of transfer of this energy. So the equation that governs this is the rate of energy, so how much energy per time, how many joules per second are we transferring in or out of the system, is equal to the area between the two systems. So the area between the system and the surrounding, and it has the change of temperature between the system and the surrounding, as well as d, which is the distance between the two. So say we have this wonderful cute little dog, put a sweater on it. Well, the sweater has some area. It also has some distance, some thickness of the sweater. So Q, as I said, was the rate of energy transferred. A is the area, so A would be the area of the sweater between the system and the surroundings. D is the thickness between the system and the surroundings. Again, we haven't quite dealt with the idea that we now have another system. We have to deal with the insulator material as well, but we'll just ignore that for the moment. But D is the thickness of our insulator. T would be the temperature change, so how warm the dog is compared to how warm the snow is, or the air around it. And last but not least, KT is some thermal constant, some thermal transfer constant that you could look up. Be careful, this is a KT, not KB. So KB is the Boltzmann constant, this is a different constant. And this equation will tell us how much energy is lost through that sweater. Well, we know dogs have fur. Fur has a different area exposed. It has a different diameter. The thickness of it has a different KT, so there's some energy lost through the fur. So if you have to deal with, say, this, where you have a dog that has little boots on, fur, maybe different types of fur, has a little coat on, then you have to deal with each one of these areas separate and figure out how much is lost through each area in a specific amount of time. Same thing happens in your house. You have walls, you have windows, you have doors, you have the roof, as all of them have different insulation characteristics, but this is how you can figure out how much energy is transferred out of your house or into your house on a cold or warm day. So not something you see too terribly often in physics, but engineering has to deal with this all the time. This is actually why you wrap somebody in those nice shiny blankets, or why EMTs will wrap someone in a shiny blanket to keep them warm, is because they're covering them with a large area. The thickness doesn't have to be that big, but the temperature, it might be a cold day out, and the little shiny blankets have a really, really high value of, or really low value of the thermal conductivity. So kind of an interesting subject, and just kind of a nice way to end our discussion of thermodynamics. And by no means is this the end of thermodynamics. There is a lot more to it, but this will be our introduction to it.